Kendra Roach, and this is my Newton's first law of motion demonstration. So for this law, we are going to demonstrate Newton's first law, which is if the total force acting on an object is zero, its center of mass continues in the same state of motion. In other words, an object at rest will remain at rest if the total force acting on it is zero, and an object in motion will remain in motion if the total force acting on it is zero. So for this demonstration, I have a cup, a card, and a quarter. So what I'm going to do is I'm going to place this note card on top of the cup and the quarter on top of the card. Now, because this object is at rest, and it would like to remain at rest, if I were to slowly pull the card, the quarter will stay on top. However, this coin has inertia, which is, it's a strong desire to stay in the place it's currently at. So if I flick the card very quickly out from under the coin, I'm able to drop the coin into the cup. So let's see if we can actually make this happen. And just like that, the amount of force I was able to use to pull the card out from underneath the coin was able to overcome the inertia that the coin had, and the coin dropped right down into the cup.
Welcome back with Newton's second law of motion. Newton's second law says acceleration equals the sum of forces acting on an object divided by the object's mass. So that essentially means that the total forces acting on an object are going to have to be greater if the mass is greater in order for acceleration to remain the same. So that law also states that acceleration, basically gaining speed or changing speed, happens when a force acts on a mass or an object. Riding your bike is a great example of this because your bike is the mass that you're trying to move, you and your bike, and you pedaling is the force behind that. So if you think about it, if there's greater mass on the bike, it's going to take more force to accelerate and get going. So for this, I chose to do a little experiment with my son. We have a bike seat on our bike. So we started out with just me on the bike, and I was able to accelerate rather quickly, able to get going at a rather easy pace. I had less mass on the bike. It was just my weight and the weight of the bike, the force of my legs pedaling it, and so acceleration took off easy. When I added my son to his bike seat, there was greater mass on the bike. I had the mass of me, the bike, and him with the same force, just my legs pedaling it. And so it took us a little bit longer to get going. And so I'll show you our two clips to show you what we found with that.
Okay, now for Newton's third law of motion. This law states that forces occur in equal and opposite pairs. Whenever object A exerts a force on object B must also be exerting force on object A. The two forces are equal in magnitude and opposite in direction. So for this law of motion, we chose to use a little Lego car that had a balloon strapped to it. And as the air rushes backwards out of the balloon, it pushes the car forward in the opposite direction with equal force. So, let me see this. For our car, we had our straw attached so we could blow up our balloon. And as our balloon pushed air out backwards, our car drove forwards. Just like that, we've got Newton's third law.